So the easiest way to think about titrations at this point, since you already have all of the fundamental understanding and mechanics to do that, is to just do them by example using a few different case studies. So the first case is always the easiest one. So that's when we have a strong acid and a strong base. So that means either the sample or the titrant is a strong acid or strong base. So the example we're talking about here is our unknown. We actually know it because we're doing this by example, but we'll pretend this is the unknown. So that's the thing down here in this beaker. We have exactly 40.0 milliliters of 0.100 molar HCl, which is a strong acid. And then in our burette up here, our titrant, that's also a strong base. So that's why this is a strong acid, strong base titration with a very precisely known concentration. And so the task here then is to produce what the data looks like and determine how we might figure out what that concentration would be, which is really the goal of a measurement like this in the lab. So the first condition that we should be able to understand is the sort of zero condition before you add anything at all. So that means when we just have the beaker of our sample, which is 40 mils of 0.1 molar HCl, how could we figure out what the pH is before we've added any titrant? So this is the sort of easiest condition, because when you have a strong acid with volume, you could understand that this is fully dissociated. That's what it means to be a strong acid. If that's fully dissociated, then 0.1 molar HCl is the same as 0.1 molar H+. So we could simply take the negative log of that to figure out what our pH is at the initial condition. That means we're just putting the pH meter inside that before we've added anything. What would we predict we would measure? So that negative log of 0.1 then just gives us a pH of 1. So we would predict for this unknown solution that if we were to put the pH meter inside that solution, we would measure an initial pH before we've started the titration of 1. So on our titration curve on the actual plot, what would that look like? Well, we just had a volume, which is our x-axis, of 0, because this is before we've added anything, and a pH of 1. So that means we could just sort of mark a point here, and I'm doing this very qualitatively, but just to illustrate the general shape as we're computing these points on the plot. So it's important to note now that when we are adding strong acid and strong base, or really any acids to bases, we've already determined that the neutralization reaction for that has a very large K. We call that Kn. And so that means what we established earlier is that anytime you add an acid or base, we can assume that reaction will go to completion. And so when we have a titration like this, then there's a point in volume space where we've added exactly enough of our titrant to completely 100% neutralize the corresponding acid or base in the unknown solution. We call that the equivalence point, and we're going to talk a lot about the equivalence point. And so the equivalence point is simply just the stoichiometric relationship between the acid and the base. And that will land right in the middle of our titration curve. So the next point that we want to talk about here is called the sort of pre-equivalence region. And the reason it's called pre-equivalence is because we're still adding less volume of our titrant than what is required to completely or 100% react or neutralize the unknown. So we're in the pre-equivalence. And we'll say that's 10 mils of the base. So to figure out what the pH is after 10 milliliters addition of this NaOH titrant, we can just first figure out, well, how many moles of strong base are we adding to the system? And then we know that OH and H plus of the strong acid are going to react 1 to 1. So we can figure out then how many moles of H plus are in the system to start with, and we can just subtract those. And whatever's left over is what's going to contribute to the pH of that solution. So the first step here is figure out what the moles of OH added. And so we have 0.1 molar NaOH, which is the same as 0.1 moles of OH per liter or per 1,000 milliliters. So I'm just shortcutting that. And then I can do dimensional analysis and say, well, that's only 10 milliliters. That'll give me that. So that equates to 1 times 10 to the minus 3 moles of hydroxide. And then similarly, we can figure out how many moles of H plus were in the original beaker of this unknown, assuming 100% dissociation of the strong acid HCl. So again, we're starting with 0.1 moles, but now H plus per 1,000 mils, but we had 40 mils in our initial volume of this solution. So that means there were initially 4 0 times 10 to the minus 3 moles of H plus. We know these things are going to react 1 to 1, so every 1 mole of OH that reacts is going to destroy one of these. So when we look at these two numbers, you can see OH is the smaller one, so that's the one that's going to run out first. So that's going to go to 0, and we're going to then subtract all of those moles, and we're going to be left with 3 times 10 to the minus 3 moles of H plus. So remember, we're trying to compute what the pH is at 10 milliliters addition of this base. Right now, we figured out how many moles of H plus are in the system. pH is negative log of the concentration of H plus. So to convert these moles to concentration, we need to divide by the volume. And in this case, it's important to know that you've changed the volume of the system. You started with 40 mils, but now we've added 10 more mils. So the new volume of the system is 50 mils. And so the concentration of H plus at that point is going to be this 3 times 10 to the minus 3 moles of H plus divided by the 10 plus 40 mils. And I'm going to say that's 1,000 mils per liter because molarity is in moles per liter. And so if we take the negative log of this number, then that'll give us a pH, which is 1.22. So what that means is on our plot here, we have slightly increased our pH. So we'll just say that's 10, and now we're maybe right here on our plot. So then the next point on the curve is the equivalence point, because we just talked about pre-equivalence volume, and when we arbitrarily were using 10 mils, but you could follow the same process for any volume that is in that pre-equivalence range, and it would have given you a different pH in that range. So remember, the equivalence point is simply the stoichiometric equivalence of the titrant with the acid. And so it's when you've added exactly enough, in this case, base or hydroxide, to completely cancel out or neutralize whatever the amount of H plus that was there to begin with. So what volume would that occur at? And actually, I wrote this as step 3, but sometimes I actually do this as step 1. It doesn't matter the sequence here, because sometimes it's really nice to know what is the equivalence volume, and then you know where that is on your plot, and then you know where pre-equivalence is and post-equivalence is. And so this is useful actually as a tactic to start with, but it doesn't matter in this example. So let's figure out, how do we understand what volume of this titrant is required to fully neutralize this? Well, if you look at this problem, we know that OH and H plus react 1 to 1. And so this becomes a known volume, a known concentration, and a known concentration, which we could think about as a M1, V1, M2, and V2 being the equivalence volume at which point that occurs. So first step here is then, what is the volume of equivalence? And then we'll think about, okay, at the equivalence, then what is the pH? So there's a couple steps here. So what that looks like as an M1V1 is exactly like I depicted here. So 40 mils of the HCl is equal to some unknown volume of the base that we need to add at 0.1. This, if you stare at this enough, this should be pretty intuitive that if you have exactly the same concentration of acid and base and they react 1 to 1, then the volume to cancel that out is going to be exactly the same as what you start with, which is what we produce here. So we need 40 mils of the titrant to reach our equivalence point. Second step then is, okay, at 40 mils, then what is our pH? So for a strong acid plus a strong base, the pH at the equivalence point is actually very straightforward, and this is born out of our conceptual understanding of acids and bases and what remains in solution at the point of equivalence. And I will keep coming back to that over and over again as we talk about more complicated case studies, because with strong acids and strong bases, we know that when we add the strong acid and the strong base together, if they are reacting exactly in proportion to each other, then all that's going to be left over is pure water. We know that's not true when we have weak acids and weak bases, but for strong acids, strong bases, you always have water. And if you just have a beaker of pure water at equivalence, then we know its pH is going to be 7 because the concentration at H plus is 10 to the minus 7. And so that's a very convenient thing, and we can look at our plot over here, and we'll just say that this is 7 right there, and we'll pop that over. So far, we have a plot that looks like this. Okay, so our sort of last region of the strong acid, strong base titration curve is then any point beyond the equivalence volume. So really, we're separated into pre-equivalence, post-equivalence, equivalence, and the sort of zero condition, the initial. There's really 4 points. So our post-equivalence will just make up some value. Any value in excess of 40 would work here. And we'll just pick 60 and work. So we already know, sort of through deduction, that it took 40 milliliters, that was our equivalence volume, to fully neutralize all of the acid that was in the system. So that means any drop beyond equivalence, we no longer have H plus as the excess. Now every drop of titrant we add, we're adding strong base as the excess. So we're adding 60 here. So it means we used up 40 of it to completely neutralize. Now we have 20 milliliters of essentially adding pure strong base to water, because remember, at 40 mils, what we had in the system exactly at equivalence was just pure water, and that's what gave us that pH of 7. Now we're going to be in excess of pH 7 because we're going to be adding strong base to water. So what that really means is we start with 60, we used up 40, which means we have 20 milliliters of excess that we're adding of that strong base. So what does that look like? Well, we still have the original concentration, 0.1 moles per 1,000 mils. So how many moles of OH do we have? Well, we multiply by that 20 mil excess. And if we solve that, if we look at the units, we would be in moles of OH. That would be the moles of excess OH. But remember, we're really trying to get to concentrations here because pH is related to the concentration of the hydronium ion in solution. So we have this much of excess moles of OH. To get to concentration of OH, we need to divide by whatever the actual volume of the solution is. So what would that be? Well, we started with 40 that in the original beaker, 40 of the sample, and now we've added 60. So that means we have a total of 100 mils that those moles of OH are swimming around within. So I'm just going to add a branch here and just write this as 40 plus 60 mils, and then this is 1,000 mils per liter. So doing this all in one sort of operation here, which turns into 2.00 times 10 to the minus 2 molar OH. But remember, this is molar OH, which we can't simply take the negative log of this to get the pH, because that's a hydronium ion, and so we need to convert this to the H plus, which we can do simply through the relationship with Kw. So Kw divided by that OH then gives us a value of 5.0 times 10 to the minus 13 molar. Now we can take the negative log of this value to get our final concentration, which gives us a pH of 12.30, which we can toss up here. We'll just say that's somewhere way up here. And so 60 to, say, here. Now you can start to see the general shape of this curve, which will look something like this. And so this is the titration curve for strong acid, strong base, where anything in this region is considered pre-equivalence. The exact amount here would be considered equivalence, and then out here this region is the post-equivalence, and then we have the condition right off the bat, which is upon addition of nothing yet. And so we've walked through all 4 conditions. Hopefully this one is pretty straightforward.